did Diane instead of Diane.
Oh, I did that too. Oh my God, it's so hard.
There's a handout there. What's left on there? Okay, so happy Friday. So looking forward to the weekend. We get to talk about some robustness in ANOVA, Crystal Wallace tests, and then some examples. And maybe if there's time, we'll talk about permutation bootstrap for ANOVA. It's kind of a side thing that we might consider. And in the examples, it's kind of be kind of a story of looking for an example to show where the assumptions have a big noticeable impact. It was a little challenging to find examples that have a smaller deviation from the assumption that it actually changes results too much, which is good in a way. That it seems to be relevant. I guess one just announcement is Annie will be away as a practice exam for education, so we'll be taking that on the Wednesday. So Dan will be doing the student presentation on there, and that's fine if. Those of you who have presentations upcoming, notice that you have a conflict of some sort, or say a job interview comes up. It's kind of hard to switch out the day before. But that said, if you had something on a Wednesday, maybe you could do it on a Monday or a Friday, or you could switch with somebody. And given the number of students, there's a little bit of leeway toward the end of the class. We could skip a week, and then somebody could do it. We'd still have enough time for everybody to do it. So just let me know. Check the schedule, particularly if you're at the very end, because there's less flexibility there to work it in. But again, a Monday or Friday could work out too. So robustness at ANOVA, right? So in the analysis of variance, in section 5.2, the book talks about an ideal model, right? So I think this, instead of an ideal model, thinking about it as what you would hope for if you were going to apply these methods. Or it's really the model that was used to derive a lot of the distribution assumptions. Why is it an F distribution? Well, it comes from exactly considering this probability model. So there's normal populations, normally distributed populations. Right. So our populations, if we made histograms for the different groups, would look kind of bell-shaped. They might overlap substantially, if there's not much of an effect, right, between them. But each histogram or normal probability plot is going to look something like that. So there's the standard deviation. The sigmas are all the same. Right. Same. So we're not going to have the situation where we have, a couple of groups that are really like this, and another one that's really spread out. That would be unequal standard deviations, and some of the assumptions about the F test wouldn't be exactly true, right? There's independence, right? The groups are independent of one another. It's not matched pairs or block. Is it something in blocking that we'll do later when things are kind of dependent in a way? But there's groups are independent, individuals are independent. And we're testing about the means, right? So of these, the book in 5.5 makes some comments about how important these different assumptions are to the F test, giving you significance levels that are near 5%. Right? So you do a 5% test. You don't want to reject more than 5% of the time if the null hypothesis is actually true. And which of these impact things differently? Of the so 5.5 in robustness. Which assumptions affect the significance level the most? If we do an F test at alpha, say 0.5 significance, critical thing is that we want the F-test to have a 5% significance. We don't reject more often than, or more often, so we're rejecting a lot more and making more errors. Right? We don't want 10%, for example. Right? So kind of at the top of the list is the independence. If there's high dependence within a group, so that everybody in one group would have a kind of very similar scores, you don't really have n sub I observations in that group effectively. Effectively, you kind of have one. Right? So what could appear to be a very large sample size and give you very large degrees of freedom for testing could really collapse. So if it's a measurement that's the same for everybody in a school or a classroom or all the employees at a company, it's not really independent. Or if there's groups of people entering and they're interacting with one another. So partly this is a design issue. If it's not independent, if individuals or groups are not independent, right, then consider other methods. And some confusion about this does show up, right? That you will see reports, I've seen them in education literature, right? Statistics education, this is Journal of Statistics Education, and every once in a while I get asked to review an article for that, and an article will come through and it says, we've tested on 500 students. Well, it's a large university and it's really 5 classrooms, right? And so part of the grades can even be group projects or something like that. So there's not really that sense of independence. And so there's randomized group designs where you really, there's a trade-off. How many groups do you have versus how many subjects per group? Right? And there's things to consider with that. There's things beyond the one-way ANOVA that would consider that explicitly. So that would be more appropriate. Right? The book says equal sigma is important, and it's most important if the smallest groups are the most different. Because if you have a small group with a very, so if there's a very unequal ends, so very unequal sigma and very unequal sample sizes, n sub i's, can distort the test. Where it just might, if the very big group has a very small standard deviation, that's going to cause the overall pool to be very small, and it's going to look like a small difference is significant. But if that other small group had a very big standard deviation, maybe it's really not so different. Right? If you had a bigger sample in that group, you would see that the mean was actually closer. But so I think if there's right. But it could go the other way. Right? It could kind of come unexpected results. Right? So equal is important, but primarily when there's a magnitude of more than 2 or 4 in standard deviations, and the ends are quite unequal. If the ends are more equal and the standard deviations are within a factor of 2 or 3, it's not as sensitive. Extreme outliers. Extreme outliers. More of a concern in small sample sizes. If you have small groups and a few extreme points, it's going to change the means, it's going to change the standard deviations, and the results can be influenced. Right? So in terms of the significance level, it might affect it, but also the results would be just sensitive to whether 1 or 2 observations are in there. So you might want to consider it anyway. Finally, the book says that normality is not so critical. So even if the data are skewed with some outliers, if you have a larger sample size, the averages are still, their sampling distributions are pretty normal, and things will work out pretty well. But again, concern is with oops, that's not too neat, is with TH, small sample sizes again, and extreme skewness. Right? So it's a lot of these things are very kind of loose, right? There's not a cutoff. Like if you have a skewness measure beyond this point for a certain sample size, you're going to have a breakdown. You could try to study this through simulation or analysis, but it's going to kind of give you the sliding scale. And to me, that means you look at the data, maybe you compare to another procedure, you look for the smallest ends and the most unequal places, and you kind of worry about it if the result is kind of middling. If the result is very strong one way or the other, there's kind of slight deviations are pulling things one way or the other, more significant, less significant than they maybe would be otherwise, but it's kind of in that middle area. You get p-values between like 0.01 and 0.10, and if there's big deviations from the assumptions, you kind of worry a little bit. One alternative we could look at for that is called Kruskal-Wallis test. Bill Kruskal and Alan Wallace. One of the most well-known and cited tests. And the idea here is we have our data Y1, Yij's. We're in a ANOVA context. We have two indexes. Yij is our set of data. I going from 1 up to I are the groups. And J going from 1 up to n sub I are the individuals that are in there. And the first thing we do with this is rank the data, all the data together. These Y sub ij data are transferred into ranks, where this little n is the total sample size across all the groups. We're going to, I guess it's a B, not a 2. Right? We're going to compute the variance of the ranks. That's sigma squared r. And that's going to be the same, right? These are the numbers 1, 2, right up to n. And so the variance of the ranks just depends on what the sample size is. It doesn't change from sample to sample. We do analysis of variance computation on the ranked data. So instead of putting the y variable in for the outcome, we put the ranked data in. This is going to give us between groups sum of squares. Sum of squares. And so there's a sum of squares for groups. You can put a little rank on the bottom to emphasize that you've done all the ranks. And so their statistic then out of that is comparing this sum of squares rank to this variance. So the Kruskal-Wallis statistic is the sum of squares for the groups for rank, right, over sigma squared among the ranks. And under a null hypothesis of equal rank average, this thing is going to have a chi-square distribution with I minus 1 degree of freedom. So their statistical work was figuring out that this would be a distribution that you could use to compare that. So on the next page, I'll write the assumption a little bit more. But so we get a statistic. The sigma squared R is the same no matter what the distribution is. This depends on the sum of squares group for ranks, how the ranks are spread across the groups. And so we're going to reject a null hypothesis that says there's going to be an equal rank average across groups if our Kruskal-Wallis statistic is greater than a chi-square random variable I minus 1 degree of freedom is 0.95. And what this probability distribution looks like, it's positive, everything's squared in it. So this would be the distribution of the null hypothesis. And we're going to reject if we're up here. Right? So if the sum of squares group for ranks is very large, meaning that the group means are very different. Right? When the sum of groups was big if the group averages were different. So if the average ranks are different, then you would conclude that there's a difference. Right? And it doesn't require strict normality, right? Because we've changed to ranks. We can have outliers, so that biggest outlier that's way out there, just get it to rank of n. That's not very different from n minus 1. So the distribution can be quite different. They can be different spreads, right? If there's, right, and the average ranks can still be kind of the same, and it'll be less sensitive to that, right? So what do you do after that, right? If you reject the H0 in ANOVA, right? If we did the ANOVA F test, then we would look at the contrast we talked about, right? So this one was the null hypothesis that the mu sub i's were constant. Then we can look at contrasts. Right? Which mean is different? Maybe you want to look at all pairs of means. Maybe you have specific hypotheses, so you'd look at those things. So some linear combination, say, of the means. One or more of those, maybe all pairs. Right? Maybe then you deal with simultaneous inference because you're doing so many different things. Right? In the Kruskal-Wallis, if you reject H0 in that Kruskal-Wallis test, then what do you do? Well, if you have a bunch of groups and you decided, okay, these groups are different in terms of their ranks, you want to know where they're different in terms of their ranks, right? So then you could do a Kruskal-Wallis test on subsets of groups. Right? So if you decided that your 7 groups, they're different somewhere, well, you could say, are these 6 different from each other? Or are these 2 different from each other? And you could use Kruskal-Wallis test on groups to get a little more focused emphasis on where they're different or not different. We also had a Wilcoxon rank sum test from the previous chapter for 2 groups. So you could use that on 2 groups to say, is that one different? Wilk says you might do composite groups, like you might take this group of 3 and this group of 2. Like if these 3 are not different from each other and these 2 are different from each other, you might combine them and then do a test. Are these 3 different from these 2? And so there'd be different follow-up things to do to try to understand it more. So it usually doesn't just stop with one test, even if you go to the Kruskal-Wallis procedure. But let's look at some examples, because I think we'll get some handle on does it make much of a difference? Or where does it make a difference by looking at it on some examples? The book also has a bunch of data examples. You know, we've talked about them. Even if we don't talk about all the data examples in class, a lot of the data sets are available. They're included to illustrate different purposes. And so we'll look at a few of them today. Any questions about? Yes?
Can the, like, Kruskal-Wallis, like, test statistic tell us anything about, like, what can it tell us in terms of comparing it to, like, the results of an analysis variance test?
So I would think that if they differ largely in results, that there's some underlying reason, right? Because if the data did come from the model, right, if the ideal model was pretty reasonable, right, and it's highly significant with one, I think it's going to be highly significant with the other. And same thing if it's very non-significant. P-values will change, but you know they won't. But if one is very significant and one is not, right, there has to be something's different in the data distributions, and changing to ranks makes some difference.
Yeah.
So
So-
could be a signal that.
Are we mostly just looking for, like, the results of the p-value, whether or not we reject HO, essentially? Okay.
That'd be the primary thing, and then figuring out, is one of these distributions really extreme with an outlier or really skew? Well, if it's really skew, we might take logs or something to get back to a better, more normal-like scale. If one of the group has a big outlier, we might do something about that. Maybe that's not a reasonable value. Right? So in any case, in some of the medical examples with lipids and triglycerides and things like that, a lot of the normal measurements could be, say, 0 to 100 or 50 to 100. But once things get out of balance in people's bodies, it shoots up past 1,000. So it could be way out there, right? And so some restriction saying we're not going to take anybody above, or we're going to cap it at 200 to make the assumptions of the test better, right? It could lead you to thinking about the underlying measurement.
So if we thought we're thinking that there's a lot of outliers, then we'd probably rather use the Kruskal-Wallis because it's based on ranks.
Yeah.
In the analysis.
Yeah. Or at least check the consistency, right? So if something happened with a note where you didn't get a significant result, maybe those outliers in one of the groups has made the variances very large, and that's kind of wiped out some of the effect, right? Because it has to overcome that big variance to get a significant effect. But maybe Kruskal-Wallis then doesn't have that problem. And there really is a mean difference, but it's no longer overshadowed by the huge variability in a couple small groups. Could help you, right? Kruskal-Wallis, when tests are named after somebody, there's often a bio out there. Here's Bill Kruskal. He passed away 2005. I thought it was later than that. But anyway, he was at Columbia and Harvard and Columbia, did things in the United States during World War II, and then went to University of Chicago, where he was his whole career. I actually met him, I had lunch with him a couple times, but it was when I was at University of Chicago for a little while. But he kind of looked like that most of the time. that looked like he was looking at, staring at you, trying to, whatever. And then Alan Wallace is this other person. He's an economist. He was at the University of Chicago in the Graduate School of Business, who formed their Center of Business, and then was president and chancellor at the University of Rochester. And he was a presidential advisor on a number of economic committees, even up to under Reagan, so that was pretty more recent. Anyway, that's more recent for my time in the case. So anyway, a little bit of interest to see who these people are. The data, so our diet data that we've used, these were the box plot of the data. Some variability doesn't look that much different, but maybe a few outliers in there. So certainly not completely ideal for the hypotheses, but in this case I would say not too extreme, right? The ANOVA gives a p-value that's very, very small. The Kruskal-Wallis, there's a Kruskal test. And if you run that, it gives the statistic, chi-square statistic of 159, and that's also extreme. So in both of these cases, they're giving you extremely small p-values. There's no question that there's a result, right? The thing about that in an article or description, if it's really a serious thing, and there, you're noting skewness somewhere and to describe the data, it just takes about half a line or a little parentheses to say Kruskal-Wallis p-value less than 0.001. And it's easy to communicate that you also looked at that extra test. The trial data, right, had this. This was the plot. And there's a little bit bigger variability in some of these, right? Maybe little outliers. The other thing about this table, judges, is that a couple of them are pretty small. Like a D is only 2 people, 2 trials, right? So sample sizes are kind of small. So the ANOVA gives a very small p-value. There's a significant difference somewhere. The Kruskal-Wallis one gives also a small p-value, but instead of being that many decimal places, zeros, instead of 4 decimal places zeros, it's 2 decimal places zeros. So it's still very small, right? You probably can't report, this one would be p less than 0.001, it would be maybe p equal 0.001. Rarely are p-values reported to more than that 3rd decimal place. Right? So it changes things a little bit, right? The mix of distributions and variances seems to make it look a little bit more significant in over, so it could make a difference, and in terms of the p-value. But the overall conclusion is not changed. There is a difference. Right? So then, because that difference, you might look at this group versus that, or by kind of both, like a linear contrast that you would follow after ANOVA, then you might follow that up with a rank sum test, because it would be responsive to the fact that there was that difference. There's this example in Chapter 6. The first one was on ratings of job applicants. And it's a study where they had people evaluate them, and then some people were showed up or presented with a handicap, right? And it was artificial. Right? So it could be the same person with or without the handicap. And let's look at the data. I'm going to do this LAS equals 2 thing to get it to shift a little bit. Some people were shown up, so no handicap, an amputee, crutches, hearing impairment, or wheelchair. And so if there's no difference in how they were treated, in this randomized study, everything would be about the same. It looks like the hearing was put down a little bit. So whether people are specifically having a bias, you don't know, but at least maybe there's an unconscious bias. And so this one, I don't really have any concerns about the distribution. The spreads are not too highly different. 1 point's marked as an outlier, but it's not so far away. So I wouldn't expect much difference at all. And 0.03 and 0.03. Right? If the results look pretty reasonable, it doesn't change very much at all. Right? It's kind of near the border, so 0.03, so it would have been, if you really want this 0.05 level standard, then it's kind of at the border, but it doesn't make one. The second case study in there, I don't know if you read that one, but it's about adding artificial tails to fish. So there's fish, and some of the species, well, there's one species of fish they're looking at, and there's another related species where the males have colorful tails, and the colorful tails are associated with reproductive success. So they took up this species that didn't have that, but was related in a way, and they either put a yellow swordtail on or a clear swordtail. So there's kind of this extra size in both cases, but one's colorful and one's not. And does this make a difference in the species where the males don't naturally do that? In terms, and so they had there's a little picture, there's an aquarium type thing, and two sides, so they could put the female in the middle and the two males on either side with the difference, right? And then see which side they go to. And so there's 6 pairs. There's some question of whether a difference is by pairs. So yes, there is a difference that the yellow swordtail, which is not natural in that species, seems to be more attractive. Maybe it's more novel, and that's the reason it's happening. I don't know, but so that's a biology question of what does that mean. But that was the box plot there. How many times do we get each of those pairs? Are any of them small? This pair 5 is a little bit smaller in sample size, certainly narrower. This one's certainly bigger in range. So some of the assumptions seem a little bit less. I think there's something to this with the number of groups too, right? So if you had this one versus this one, right, and that was the only 2 groups, then it would look like, boy, that's extreme, right? And the 2-sample t-test, we would definitely want to look at it with unequal variances and maybe the rank sum test. But there's something to having a bunch of other groups that are kind of intermediate, right? It kind of, the overall effect of one small group is kind of less if there's more groups. I don't have a specific source to say that, but it has, I think it ameliorates it to some degree. Right? So those are the pairs. The ANOVA gives a p-value that's not significant, and the Kruskal also is not significant, right? There's not much difference here. It changes the p-value, 0.56, so things change a little bit, but not so extreme. So again, we're kind of looking for an example where it makes a big difference that we really care about. Yeah?
So say we have an example, I think the homework has an example similar to this, where it's like the box plots are, there's like a bunch of outliers for each group, but like the outliers are kind of in the same spots, but among each of the groups. Should that result in like a difference? Would that still lead to a result in the difference between the Kruskal-Wallis and the analysis of variance, or like because the outliers are in the same spot, would both tests kind of yield the same?
So I think because they're kind of in the same spot, that it's not going to create that big of a difference, right? In part because the measurements of variance, like the within group variance, is going to be similar, right? That they're all going to be made a little bit bigger and kind of similar big because of those few outliers up there. If there's one had a big outlier going negative and another big, going that would be a shift in means. But if like one of them, a few of them had big outliers and some of them different, then that kind of the pooled variance estimate gets kind of funny, right? So it's, but this case doesn't seem to make much of a difference. There was a chapter 3. There was a data example that essentially asked whether the T-Rex dinosaur, Tyrannosaurus dinosaur, was warm-blooded, right? And it's kind of interesting, right? They looked at isotopes in the blood. Did I write that down? Did I put it in here? Right. So here's the, I did write something. So the oxygen isotope composition in the bone phosphate. So they have a sample from bones, and the isotope composition is affected by body temperature. So they have a measurement that's sensitive to body temperature, and they have 12 bones in one specimen. So if it's cold-blooded, the bones in the interior have different temperatures than the bones in the exterior, closer to the surface, right? So bones will have different phosphates composition in cold-blooded animals, but in warm-blooded, it's more constant, right? So they're a negative. If you don't reject a difference, that suggests warm-blooded, but if you do reject variability, equal means, then that suggests cold-blooded, right? So there's only one dinosaur specimen. Here's the box plot of the bones. And I've done something here. The original data had bone 1, bone 10, bone 11. if you did the original order of the bones, it would come out like this, right? Because there's bone one, bone, because doing it alphabetical. So I changed those factors to have different levels. And, 1, 2, 3, 4, and put them in B1, B2, B3. So I changed their levels to, I think that's, would be, I might have messed things up. But in any case, I'm just going to leave it like that for now. And what do we see? Pretty big variability in bone phosphate compositions, right? So that suggests that T-Rex was cold-blooded, right? Because some bones get a lot cooler than others. There is bigger variability in those. They're pretty small sample sizes, so we might be concerned about that. So what are the different tests show us? ANOVA is very significant. Kruskal-Wallis is very significant. But again, it's lost a few of its zeros, so it's not quite as much. Okay, we're still looking for something that changes results. One data set we didn't talk about that's in there is data on the Challenger accident, the Challenger explosion. So that was 1986. It's actually his birthday, but we were watching it live in school, but that's okay. And so this one has, this is what the data looks like for this one. And how big is it? So there were, the launch, whether it was cool or warm, set at 65 degrees, right? So they're launching in Florida, and some nights in Florida, some days it would get cold. And one component of the launch for the space shuttle, it goes up on a big rocket with the shuttle attached to it, and then eventually the shuttle flies around and then lands on its own. But in the gap between the liquid fuel cells, right, the rocket fuel, are these O-rings, these plastic rubber O-ring things, right, that are supposed to stop leaks. Right? This is a huge explosion to get them going, right? And so if those fail, then the fluid leaks out and it blows up. But rubber or plastic or things in extreme cold is more likely to crack. Right? You get a temperature differential, cold versus hot. And so they monitor each of these O-rings, and so the number of cracks or incidents, not at full breaks, but even just cracks are a concern. And so this little data set, the data looks a little funny in this. There were just 4 launches where it was cooler than 65 degrees, and then there was a warmer one. And there were a few that had O-ring cracks or breaks in warmer launches, but cool. Your table, see that there's just 4 and 20. The ANOVA there is very significant, and the Kruskal-Wallis is still significant. So it does not look like the ideal model in any way. The data themselves are 0, 1, 2s up to 3s, but you could try to apply ANOVA to this. I guess one reason we didn't really talk about that data set too much back in chapter 4 is it doesn't, to me, seem like this is really a great way to approach the problem. One of the conceptual questions that's in the book. So there this was in chapter 6. This O-ring data, right? The case study in this involved a number of O-ring events on U.S. space shuttle flights. Launch temperature above and below. In the context of the chapter, is anything suspicious about this data? Is there possible data snooping? Right? Is how it phrases it. So they called warm if it's above 65 and cool if it's below 65. So why 65? If you had the engineers and chemists say, well, that's a critical temperature for this plastic or this rubber, right? Then that's one thing. But if you just have a bunch of data, and you say, oh, that looks like a split, right? Then that's a little bit, artificial. Maybe there's not a natural split there in terms of performance and so on. So it's a little bit kind of choosing a cut point, right? So if you did, oh, well, there's one at 67 that also had a failure. Maybe I'll split at 68. And then there's more failures below and less failures above. So it kind of, that gets that feeling that they've made that decision after looking at the data. So just in terms of this investigation, in terms of the output, again, it didn't actually make much of a difference, even though the distribution is so extreme. It's kind of interesting that it didn't. But it's possible to do really evaluating this, it's a much harder question because there's small data sets and it's very sparse, right? And there's a lot of factors going on. So there's a journal called Statistica Sinica. It's a statistical journal out of the Taiwanese Statistical Society. It's free and online, which is awesome. And so you can get all the past issues in terms of 2019. There was an issue in 2018 on modeling and predicting extrapolated probabilities of outlook. So it's about predicting the space shuttle disaster with methods, different methods, right? And so you can get that article for free. Can I open it somewhere? Let me see. So you can download the whole thing. It's about 6 megabytes. So I'm not going to put that on the website, but it's there. The conditional probability of an adverse outcome from a set of covariates. Right? They often have to extrapolate outside the range. And when the disaster actually happened, it was colder by a significant amount than any other test. So it was an extrapolation. And so down here somewhere, right, here's all the statistical methods of outlooks and different things. And what's the whole point? We'll get to something that we can look at. So there's the challenge or disaster. So the catastrophe was due to the breach in a field joint of the booster rocket called this O-ring. Previously, they had launched at 53 degrees. On that day, it was 31 degrees in Florida when they launched. Right? And they thought, they're kind of extrapolating. No, we don't think there's going to be a problem, even though we've seen cracks at 50 and 63. So it's a bigger thing. And so there's, they have this probability plot, the expected number of incidents versus temperature in degrees, but rescaled to 81 minus. So this is 81 degrees and 71 and 61 and 51. And they were out here at, right? And then so it's really extrapolating this data from this point. The real application is extrapolating data back here to clear outside the range and seeing what in the world would happen. So that's why it's unclear that standard methods, ANOVA or anything else, would seem to really apply. So anyway, that's what the data is, and they do a bunch of more advanced things. Toward the end of this class, once we do logistic regression and a few things, some of the methods they talk about there were in there. I actually wrote a comment on that. There I am. I was at Iowa State University at the time, and so this is a statistical likelihood, the Bayesian analysis. And if we had information from the engineers or tests outside of actual launches that would give some information about failures, we should try to use that. Right? So it's a Bayesian, there's a probability model there. And so you can fit this logistic regression, right, on it there. But the idea is that there was a low and high. Well, maybe the material operates differently at high temperatures. That between 65 and 100 degrees, there's really no difference in terms of its security. But below a certain threshold, below 50 degrees, below, some way down there, it operates differently. It's more likely to crack. So you could augment this thing with a mixture model. Mixture models was something I looked at in different applications over the years. So a mixture model, but we don't have enough information to actually estimate this. I read some of the reports, the congressional hearings that talked about that, and the engineering evidence about that, about where they thought it would break. And so you can come up with kind of pseudo data. It's not real data, but kind of a high probability of failure, low, and so on. And under different simulation, different prior information that you would incorporate, come up with probabilities of failure in the failure in component 1. So that would be I don't remember exactly what it was. But there's 5% intervals for failure probabilities under different assumptions. And so at 31 degrees, there's a really non-trivial chance under any of these models. And that's a number of the other authors come up with something like that. That if you modeled it with these ways that kind of think about extrapolation, you get big uncertainty, but you also get a pretty high chance, a very high possible chance of failure. So in any case, that's available and it's an interesting application. And I'm not sure I would use this one with ANOVA as a primary example. I would actually look at the temperatures to do it. So it's an interesting example, and kind of interesting that Kruskal-Wallis doesn't give any different conclusion. But that doesn't mean that either one would be a preferred analysis for that. In any case, this is one of the journals that is online and free, which is pretty amazing. Let's return briefly to looking for another example where it makes some difference. So under the Kruskal-Wallis help file, they mentioned a couple data sets down below as examples. And one is about air quality in New York City, and again, that one doesn't make too much difference. But even though the standard deviations are quite different, there's some outliers. The Kruskal-Wallis or ANOVA still gives kind of the same thing. So I thought, well, maybe this other one's up here, so it shows the usefulness of that. So Hollander and Wolf is a book on non-parametric statistics, so statistical methods. We don't make as many assumptions like Kruskal-Wallis or rank sum. And there's some, so an efficiency, a rate of removal of dust in normal subjects, subjects with obstructive airway disease and subjects with asbestosis. So these are individuals with asbestosis have been exposed to asbestos, so it's infected their lungs and they're having problems. Right? So there's some data. I don't know all the measurement issues involved here, but there's that. We do a Kruskal-Wallis test that says there is not a significant difference between those groups. Let's look at the data. These are what the data look like. Well, the only assumption that seems violated is unequal standard deviations. Right? This one looks a little bit bigger, but a priori, I wouldn't, based on this experience of looking at a bunch of examples, wouldn't think it's going to make much difference. And it doesn't, right, for ANOVA. ANOVA, you still get very significant, p-value 0.19, this one was 0.68. So those p-values change a lot, but they're both still not significant. Right? You couldn't say that. But what if you change the data? So this is where I wanted to find an example. Right? So I made one of these 34 instead of 3.4. It's a typo, right? You get a big data. And I added 1 so that I'd make the means different. So just a little altering there, right? So if you change those, right? And let's look at the new data. Right? The new data looks like that, right? So that one is 34, and it's also shifted up a little bit, so it distorts things pretty severely. Right? The Kruskal test with the new data gives a p-value that's significant, but with ANOVA, it's not significant. So did I run all these again? Let me just make sure I got through all that. Kruskal test is significant, but the ANOVA one is not. And that is the right box one. Right? So this is one case where Kruskal gives a significant result, but ANOVA doesn't. that one big outlier makes the pooled variance so large that this small mean difference no longer looks to be anything but chance, right? So that's admittedly extreme picture, right? And that is, I made it as an outlier, so you would hopefully find that and correct it. But at least in certain severe cases, it does make a difference, and hopefully that helps you find something. I played with this, so if you have a big difference like this one, make it a 5 there. The Kruskal test is still significant. The ANOVA is not quite significant, even though, right, it's a bigger shift. Right? You look at this versus that, it looks like a big shift. If it wasn't for that one outlier, even where there's a difference of about 5 on average, it's not picking it up. Right? So if you were doing kind of a high throughput statistical evaluation, where every day or every week or something you need to evaluate something, and at some point something came through an outlier, and you're just doing ANOVA, you would say some things are not significant. And maybe if you're monitoring the process quality over time, and you would miss it one week, when things really kind of got out of balance, and it would be due to this outlier kind of making the variance look so big. So it can happen, but for many of the examples that are in the book, they're not extreme enough to make a big difference. So I guess you can report both things and it's going to be consistent. Or if you moved ahead with ANOVA and did contrasts, it would seem to be a fairly reasonable thing to do. But there are methods that deal with even, I think Kruskal-Wallis would suggest that this really is a significant difference, and we, based on this picture, would think that, yeah, that does seem different. We hope to reject. That's it. I think, maybe I'll come back and say something about the permutation ANOVA, but that's kind of what we have for. Well, we do have time, right? We did at 10:40, so right. Maybe we'll do that just to be able to go on to something new on Monday. But any questions about this comparison? Right. So I just wanted to mention, that we've done the test this hypothesis, right? But we also looked at some bootstrap things or permutation tests with 1 and 2 samples. You can evaluate this with a permutation test that does not require normality. So how would you generate a sampling distribution for our F statistic? We're going to calculate our F statistic in the usual way. But we don't have the ideal model. Maybe we don't want to compare that to an F distribution, because after all, the core assumptions were that normality and so on, right? Equal variances. So if there is no effect of group, right, then the sorting of subjects into groups is effectively random. Their outcome measure, if there's no group effect, anybody from the different groups could have had any of the outcomes. So one way we could simulate the distribution of the F statistic, so we want to simulate the distribution of F. So I'll write that on the next page, so there's a little more space. But we're going to simulate that distribution as F statistic. So instead of relying on the parametric F distribution function, we're going to simulate it. Simulate 10,000 values and see if our value is extreme. So how can we do this? We're going to put all data together. N1 plus N2 plus N sub I cases all together. So we have all their Yij's together. And then to get a random permutation of these things, right, we're going to randomly pick N1, the power replacement, from the data. And that's going to be our group 1. And we would do kind of we could do a new group average based on that. Then out of those that are left, we're going to pick N2, right, and call that group 2. Randomly pick N2 without replacement from the others. This is your ROUP. And that's going to be our new group 2 in simulation. That'll give us a new bar. And then we keep doing that. And then the last N sub I are taken as group 3. Groups are group I. And that would give us another average over here. We also have the individual data that we've reassigned to those things. And then we can calculate an F. Calculate our value of our F statistic. Right? If we do that whole process, 1,000 times, we have 1,000 values of the F star statistic consistent with the hypothesis that there's no difference. So this whole thing, right, say kind of B equals, say, 1,000 times. And if our statistic on our F statistic on our actual data is very large, we'll reject it. Right? We don't have to use normality or the F distribution. If the model is about appropriate, right, if it's not too bad, the simulation probably will give you quite similar results. Right? And you would reject under either one. But this one shouldn't be sensitive to that. Right? I don't see it talked about or implemented so much, but these simulation ideas, right, can be extended to other cases. And so just felt like talking about that. So, a little bit, so. Not that we're going to do anything more with that, but it's possible to do those things. So. Okay, well, have a good weekend. We'll come back, and I think next up is really talking about linear regression.
Thank you.
No, Diane. So Dan, if you have any questions?
Yeah.
About office hours Monday, Tuesday. So.
I was thinking I was going to look at it tonight, so probably Monday. I'll stop in and ask some questions.
Sure. There's one example, and
Okay.
that online book that's mentioned on the page. They have a data set,
Okay.
or maybe I made the data sets and put them on there. So that'd be one option.
Yeah,
So
definitely.
it doesn't necessarily have to make a much of a difference, but it's kind of showing
Yeah,
some of those
Definitely.
translation issues.
definitely. Thank you.
Cool. Yep.
See ya.
Yep.
Are you the one?